Basically, it helps us create virtual machines on our desktop or laptops. To install VirtualBox, we will go to a browser and search for VirtualBox. We'll then click on the download link, and here we should be able to see all the packages listed for the different operating systems. To verify that VirtualBox is successfully installed on our system, we'll search for the vbox commands on our system. We can do that by typing vbox and then pressing the tab keys, and there we should be able to see the two vbox commands. That's all we need to do to have VirtualBox ready for this course. The next tool we are going to install is Vagrant. Vagrant is a tool for building complete development environments and is completely open source. This tool is exceptionally helpful for developers and admins to set up development environments within a couple of minutes and with minimal configurations. We will configure 3 virtual machines for initially starting this course. Our environment will consist of 1 Puppet Master and 2 Puppet Agent nodes. One of the agent nodes will be a CentOS 7 virtual machine, and the other one will be a VM running Ubuntu 16.04 LTS. We will configure a heterogeneous infrastructure to demonstrate the capabilities of Puppet in managing a truly diverse environment. To download Vagrant, we need to go to a browser and search for Vagrant, and we should look for the first option that's here, which is at vagrantup.com. We need to go to the downloads page for the same, and here we have the different packages available for the different operating systems. Once Vagrant is installed, we can verify this by running the Vagrant command along with the version option, and there it tells us that we are running an up-to-date version of Vagrant. The next thing we need to do is we need to initialize a Vagrant configuration file by running the Vagrant init command. Once we do this, we should have a Vagrant file available to us. The next thing we do is open the Vagrant file in an editor, and there we see a lot of options with descriptions available for us. But for our purpose, we are going to delete all the options available here, and we are going to configure our virtual machines from scratch. All Vagrant configurations should be between the vagrant.configure parameter and the end parameter that is defined here. The first thing we are going to do here is tell Vagrant which provider to use to create virtual machines. For this, we'll be adding a block called config.vm.provider, and we'll specify that we are going to use the VirtualBox provider for the same, and then we are going to end this block with the end parameter. We'll then define the CPU and the memory that we want defined for our virtual machines. So basically what we have defined here is that we tell Vagrant that we'll be using the VirtualBox provider to create the virtual machines, and each VM should have 2 GB of RAM and 2 virtual CPUs available to them. The next thing we are going to do is start configuring our virtual machines themselves. For this, we need to create a new block called config.vm.define, and then we will provide a name for the virtual machine, which is Puppet Master, and then we will add another identifier. This identifier called PM can be anything you wish. We have just added PM because we call this virtual machine the Puppet Master. And we will end this block with the end parameter, and then we will start adding our configs in between. The first config will be the box name from which this virtual machine will be created. This is called pm.vm.box, and the box name will be CentOS/7 because this will be a CentOS VM with the CentOS 7 version. The next option that we'll have here is a pm.vm.network. This will basically define that we will have a private network with an IP address of 192.168.33.10, and the last option that we'll configure here is the host name, which will be Puppet Master, and there we have our first virtual machine configured in the Vagrant file. So basically what we have told Vagrant here is that we have a new virtual machine called Puppet Master, which will be launched with the box called CentOS 7. It will have a private network interface with the IP address of 192.168.33.10, and the host name should be configured to Puppet Master. The next thing we will do here is replicate this block a couple of more times, because we have 2 more agent nodes to configure for our infrastructure. The first agent will be called Puppet Agent CentOS. It will again be a CentOS 7 virtual machine with a different IP address. For clarity's sake, we will add the identifier as PAC because it's a Puppet Agent CentOS. And we will also need to change this identifiers from PM to PAC. And also we will be changing the host name for the virtual machine. We will change it to CentOS Agent, and we will do the same with the third node. It will be called Puppet Agent Ubuntu, and we will change the identifier to PAU. And we will change the box name to Ubuntu/Zenile64 because that's the code name for the Ubuntu 16.04 LTS version operating system. We will have a new IP address for the VM here, which is 33.12. And finally, we will change the host name to Ubuntu Agent, and there we have our Vagrant file ready for use. The next thing we are going to do is see a quick status of our Vagrant environment. We will run Vagrant status, and the output should tell us that we have 3 virtual machines configured using the VirtualBox provider, and they're all in power off stage. So the next thing we are going to do is get them up and running with Vagrant up. And there we see all the VMs getting started. We will pause the video here and let the VMs come up. Once the VMs are up and running, we can test them again using the Vagrant status command. And here it should tell us that all our VMs are running. What we can quickly do here is check our access to the servers by running Vagrant SSH Puppet Master. And Vagrant should log us into the virtual machine using SSH. A good thing to note here is that in Vagrant, we do not need to remember usernames or passwords. Vagrant takes care of that for us, and we just need to use the Vagrant SSH command, and it does log us into the virtual machine using the Vagrant user, and then we can run the sudo su command to change into the root or the admin user. That's all we need to get up and running with Vagrant for the purpose of this course. The final tool that we will install for our course is the Atom editor. There are numerous editors out there, and all of them have their pros and cons. It really depends on what we are looking for in an editor. Atom is a really simple editor which is easy to use and is gaining popularity among developers worldwide. To download Atom, we need to go to the browser and go to atom.io, which is the official page for the Atom editor. And there we can go ahead and download the package for Atom. Once we have Atom installed, it should look something like this. The next thing that we need to do for Atom is install a package called language-puppet. The Atom command line binary is APM, and we can install the package using APM install, and the package is called language-puppet. And this will install the language puppet package for Atom for us. So what basically this package does is provide formatting support for the Puppet DSL in the Atom editor. So that's all we need to get up and running with Atom. for the purpose of this course. The last step in the install and setup stage is to set up an account on GitHub. If you're not aware what GitHub is, it is an online project hosting service for version-controlled repositories using Git. To create an account on GitHub, we need to go to github.com and we need to sign up for an account. So we need to pick a username here. So we can name it extending Puppet. The email address will be extending.puppet.course@gmail.com. And I'll provide a password here. And then we can sign up for GitHub. We will register for a free public repository plan. We are going to look at what configuration management is and how Puppet fits into the scenario. Next, we are going to look at the different Puppet components and terminologies. We will then go on to understand what happens when the Puppet run cycle takes place. Then, we are going to move on to installing the different Puppet components. And finally, we are going to have an overview of the Puppet domain-specific language. In this video, we will learn about what configuration management means, the benefits of configuration management, the things to keep in mind when choosing a config management tool, and finally, we will learn about the position of Puppet in the ecosystem. Let us first understand what configuration management means. Configuration management is the process of maintaining the state of a system or an application. It involves configuration of a component, implementing and tracking changes made to that component, and maintaining an integrity with the rest of the infrastructure. There are two types of configuration management. The first one is software configuration management, which involves management and automation of application development. This process involves a software project and is out of scope for the purpose of this course. Another type of configuration management is system or server configuration management, which involves configuration and management of server infrastructure through automation. In this course, our focus will be on server configuration management. Let us now discuss the benefits of configuration management. Why make the effort to get into this new concept? Config management makes building new servers a breeze. Gone are the days when one had to install the operating system on a farm of few hundred servers and then had to run scripts to configure packages and services on them. And there were always chances of mistakes, missed changes due to hardware or network glitches, and there were no easy way to track all of them. With config management, all these beasts can be tamed with various levels of complexities. With config management, the state of the infrastructure can be efficiently maintained in a version-controlled manner. A modular approach to manage services integrated with version control systems like Git provides a strong control on the infrastructure. Config management provides control of the entire infrastructure from a central server with the independence and ability to push changes as and when required on a specifically targeted set of servers by use of orchestration. Creating new environments or entirely new data centers is a minimal task with config management when coupled with proper architecture design and deployment procedures. Next, let's look at the things to consider when we want to select a tool for config management. Complexity of the tool and the infrastructure are the first things to consider when choosing a tool. The scale of the infrastructure, the number of services to manage, the interconnectivity of the services, the diversity of the infrastructure are all vital factors. The capability of the tool to handle complex infrastructures should be the foremost consideration. However, the complexity of the tool and the learning curve to master it should not be ignored at the same time. Cost of the tool comes next. Most config management tools have free open source and premium enterprise versions. To get started and check the offerings of a tool, the open source version is a great option in most cases. Although large infrastructures can be managed by just using the open source versions, often there are valuable options available with enterprise versions and should be checked out. Support is a vital requirement for many organizations. For open source projects and versions, usually the support is in the form of community forums and public channels, but dedicated and premium support mostly do come with enterprise plans for the tools. Finally, we will look into where Puppet fits in the conflict management scenario. Puppet is one of the oldest tools of conflict management. It was initially released in 2005 and has been one of the strongest and widely used software for conflict management in organizations of various sizes. Although the open source version of Puppet is mostly used by organizations, the enterprise version of Puppet boasts features such as high availability, orchestration, visualization, reporting, and much more with minimal effort of configuration. Puppet, being one of the most experienced tools available, has a massive community of code committers, public module creators, and online forums for help. Learn and get familiar with the various components and terminologies of the Puppet ecosystem. We will look at some of the most important components and get a generic understanding of the same. We will learn about the generic architecture of a Puppet infrastructure, understand the software components of Puppet, understand the role-based terminologies of Puppet, and finally understand some components of the Puppet language. The Puppet architecture is basically a client-server model. The first component that we'll look at is the Puppet master. In a standard Puppet client-server deployment, the server is known as the Puppet master. When Puppet agents are executed, they connect to the Puppet master, and the master compiles and serves configuration catalogs to the agents using an HTTP server. The ideal way to run a Puppet master in production is with a web server or with the Puppet server. Puppet server is an open source Java virtual machine application that provides high performance and scalable Puppet master services. It can be termed as an alternative to the web server, which needs to be deployed to serve the Puppet master services to the agents. It also provides an API used for administration purposes. Puppet DB. Puppet DB is an open source database that caches and stores data generated by Puppet. All the data that are collected from Puppet runs on the infrastructure are stored in Puppet DB, which can then be queried through an API provided by Puppet DB. Puppet agent. Puppet agents are daemons which run on client nodes and connect to the Puppet master to request compiled catalogs which correspond to it. The agents can be run continuously as a daemon, or they can be scheduled to run at certain intervals by using schedulers such as cron. Factors and facts. Facts are information of a node or server which are populated by a tool called factor. These facts are then sent to the Puppet master by the Puppet agents when requesting compiled catalogs and are evaluated by the Puppet master against the manifests. Puppet run. A Puppet run takes place when a Puppet agent contacts the Puppet master to request compiled catalogs by sending facts and then applies that catalog to the node on which it is running. Puppet language. Puppet language is a domain-specific language which are written in the form of manifests with the .pp file extension. These files are then compiled by the Puppet master during a Puppet run, and a catalog is provided to the Puppet agents to be applied on the client servers. External node classifiers. External node classifiers, or ENCs, are scripts or data sources which tells the Puppet master about which manifests are to be applied to a node. External node classifiers can be scripts in different programming languages, an LDAP database, or Puppet DB. The ENC is provided with the node name, and a YAML document is provided by the ENC in return, describing the manifests to be applied to the node. Manifest. Manifests can be defined as Puppet program files which are written in the Puppet domain-specific language, or DSL, and are named with the .pp extension. In most cases, manifests are contained in modules and are written by defining classes, types, and functions. Resource. Resource is a configurable entity that can be managed by Puppet. Every resource has to be defined by their type and identify a name, various attributes, and their respective values. They can be packages, services, or files. Type. Types are kind of resources that can be managed by Puppet. Each resource has a type which defines the attributes that can be used with that type and its behavior on the target systems. There are quite a few types which are built into Puppet, and many more types can be added by writing plugins or by grouping together resources of existing types. Provider. Providers are components which decides the system-specific tool to be used on the target system for a defined resource type. Providers are basically short Ruby wrapper scripts built on native commands, and new ones can be easily created. In this video, we will get into details about how the Puppet components work with each other, learn about the certificate-based authentication of Puppet agents with the Puppet server, go through details of the Puppet run cycle, and have an understanding of configuring a Puppet manifest. The Puppet server is a Java virtual machine application and provides the Puppet master service. It can be configured on a CentOS or Ubuntu Linux operating system and requires the Puppet server package to be installed. This is an example of a Puppet manifest written in a manifest file called webserver.pp. The entire code is written in the Puppet domain-specific language and is enclosed in a class block. The parameter based on which we are setting a condition, that is OS family, is a fact sent to the master by the agent using factor. The ensure here is called an attribute which is specific to a resource definition. The package block is known as a resource definition, and the package itself is called a type. Next, we will look at the Puppet run cycle. The Puppet server, which contains the manifests that we have already configured, is also a certificate authority. It is connected to a Puppet DB, which stores and caches Puppet data. It is also connected to an external node classifier or ENC, which is used to fetch node definitions. We have two Puppet agents here. We will demonstrate the communication between one node and the master. However, it must be assumed that the other node will also do the same. There are two steps of the run cycle. The first one is authentication. All Puppet communication between the server and the agents take place through Secure Socket Layer or SSL. The Puppet server also acts as a certificate authority which signs certificate requests from the clients. This prevents agents to request catalogs from rogue servers and servers providing catalogs to rogue clients. The agent makes a client certificate request to the Puppet master, which the server needs to sign before any further communication can take place. The request can be signed manually or the process can be automated. Once the server signs the request, a successful authentication takes place and the channel is ready for further communications. Once authentication is completed, the agent makes a catalog request to the server. Puppet server contacts the external node classifier or the ENC to get the node definitions for the agent. The ENC responds with the required data and the Puppet server compiles the catalog for the agent. The agent receives the compiled catalog and applies it to the nodes. Providers on the nodes use the correct package manager for the respective nodes and install the package. Once the catalog is applied, the node reports back to the master about the result of the transaction. Finally, the Puppet server saves the data in Puppet DB, which can be viewed. In this video, we will learn about the installation process of the different Puppet components on the Puppet servers and clients, and then explore the directory structure of Puppet. The Puppet master in our infrastructure is a CentOS operating system, and one of our Puppet agents is also a CentOS. To install packages for CentOS, we need to go to yum.puppetlabs.com. The first thing we need to do is get the Puppet repositories on our systems. To do this, we need to copy the link to the RPM for the specific architecture, that is Enterprise Linux 7, and then we need to install the RPM on our systems with the RPM i-ihv command and the full URL of the RPM. We're going to do the same on our CentOS agent node. Once we have our Puppet repositories on the Puppet master, we need to run the yum-y install Puppet server command to install the Puppet server. This is going to take quite a lot of time. So we are going to go to the ZenOS agent and start installing the Puppet agent. We're going to get back when it's done installing the packages. For our Ubuntu agent, we need to go to apt.puppetlabs.com and we need to get the address for the Debian package which creates a repository on the system. On the node, we need to fetch the package with the wget command, and then we need to install the package with the dpkg command. And once this is done, we need to run apt-get update. Once this is completed, we need to run apt-get install Puppet agent. We're going to get back when this is done installing. Once the packages are installed, we can see that the Puppet binary is not in our path. The reason for this is the Puppet binaries are installed in the location opt Puppet Labs bin, and there are a few other binaries which are installed in opt Puppet Labs puppet/bin. So what we need to do is we need to add them to our path variable. For this, we need to go to the profile.d directory, and the package should have already created a file called puppet-agent.sh. We need to open this file, and we can see that it has already exported a new path variable with opt Puppet Labs bin path. What we need to do is we need to add another path here for opt Puppet Labs Puppet bin. We need to do this on all our systems, and once this is done, we'll log out, and once we log in again, we should have the Puppet binary available. Once the packages are installed, we can check this with the rpm-q Puppet agent command, and here we can see that the Puppet agent package version 1.9.3 has been installed. This is a bit confusing because 1.9.3 is just the version of the Puppet agent package. The version of Puppet that is available to us is actually 4.9.4. Now that our packages are installed, the next thing we will do is explore the Puppet directory structure. The main configuration directory of Puppet is etc/Puppet Labs. We see a number of directories here. The first directory, that is code, contains all our Puppet environment and module manifests. In the environments directory, a default environment is created, which is production. Any agent which requests a catalog from the Puppet server will get all its modules applied from the production environment by default. The modules directory contains modules which are not specific to a particular environment. The next directory we can look at is the etc Puppet Labs Puppet directory. This directory contains global configuration files for Puppet Hira and also a directory for SSL certificates. The etc Puppet Labs Puppet server directory contains global configuration files specific to the Puppet server service. Most of these files do not need to be changed for optimal Puppet server configuration. There are a couple of other files which can be found at etc sysconfig puppet, which is a parameter file for the Puppet service, and there's another file called etc sysconfig puppet server, which has environment specific parameters for the Puppet server service. Another important directory to look at is the opt Puppet Labs directory. All data files and binary files related to Factor, Puppet, and the Puppet server can be found. In this video, we will configure and run the Puppet components, learn to write a basic module, and then apply the same on the Puppet agents. The first thing we are going to do here is start the Puppet server daemon. To do this, the first thing we are going to check is the file sysconfig Puppet server. This file has a lot of parameters which can be configured for our Puppet server service. One of the most important parameter is the Java arguments. For now, we are not gonna change anything here. The next thing we are gonna do is start the Puppet server service. For this, we are gonna run the command systemctl start Puppet server. Depending on the system and the memory available, this is gonna take some time. Once the Puppet server process is started, we are going to verify this by running the ps command. And there we see our service running. And the next thing we are going to check is by running the netstat command. And there we see our system is listening on port 8140. So this means our Puppet server service is running and is ready to listen to Puppet agent requests. When the Puppet server is installed for the first time, it has a default environment called the production environment. So the first thing we are going to do is go to etc Puppet Labs code environments production. So here we are in the environment production. So the next thing we are going to do is go to the manifest directory and create a file called site.pp. This file contains node definitions for agents in our infrastructure. We are going to add a node definition here. What we have done here is that we have created a node definition which tells Puppet that any agent which requests a catalog and has the word agent in its name will be provided with a catalog containing the web server module. The site.pp file can be configured with various types of regular expressions to match nodes. However, as the size and complexity of the infrastructure increases, managing the sites.pp file might become a problem. This is where external node classifiers come into the scenario. The ENCs are a much more efficient way of storing node definitions. Next, we will create a module called web server. Next, to create the web server module, we'll go to the modules directory in the production environment. And here we will create a directory called manifests and a subdirectory. We will create a directory called web server and a subdirectory called manifests. In the manifests directory, we'll create a file called init.pp. And we will add the following manifests into the file. This manifest tells Puppet to install the HTTPD package if the OS family fact of the agent is Red Hat, and to install the Apache 2 package if the OS family fact is Debian. We will then save this file. Once the module is configured, it should be already available through the Puppet server without any daemon restarts. Now that our Puppet master is running and ready with a configured module, we will run the Puppet agents on the client nodes to communicate with the server. We have already configured a name resolution for the Puppet master on the agent nodes in the etc hosts file. Another thing we are going to look at here are the facts. Facts are granular information about the system which are collected by Factor. The Factor package gets installed as a dependency along with the Puppet agent package. To see the facts available, we have to run the command factor. When the agent connects to the master, all these facts are sent along with the catalog request based on which the server applies the manifest. The format of the facts are sometimes in the form of hashes. If we want to see the OS hash, we can run the factor OS command, and this returns a hash of detailed information. If we want to specifically see the family fact, we can run factor os.family, and there we have the OS family fact, that is Red Hat. The next thing we are going to do is run the following command, which is puppet agent --test, and we will mention the server which it needs to connect to. What happened here is that a new certificate was created for the agent and the server was contacted and a certificate signing request was created. The next step is to sign the certificate on the server for this agent. To do this, we go to the Puppet master and we run the command puppet cert list. This command gives us the output which says that a pending certificate signing request exists for the agent called CentOS agent. So what we are going to do is now we are going to sign this request manually with a command called puppet cert sign and then the agent name. So what happens here is that the puppet master verifies and signs this certificate request from the puppet-agent node. Now that the agent has been authenticated and all communication channels are clear, the next thing we are going to do is run the puppet agent to fetch and apply the catalog for this agent. To do this, we are going to run the puppet agent command with test and the server name. What basically happened here is that the agent received the catalog for itself and applied it on the node and installed the HTTPD package. Another thing to keep in mind is that if we need to verify first as to what changes are being applied on our system before actually applying them, we can do so by adding the --no-op option to the Puppet agent command. Let's try this on the Ubuntu agent node. For this, we are going to run the Puppet agent --test --server puppet master.local, and we will add an extra option called --no-op. The output tells us about the changes that would have been applied to the node if the no-op option was not set in the command. Let us now remove the no-op option and see what happens. We can see that the app provider has installed the Apache 2 package on the Ubuntu node. The final thing we are going to look at before wrapping up this video are the reports. If we navigate to the /opt Puppet Lab server data Puppet server reports directory on the Puppet master, we can see that reports have been generated for the two agent nodes that we have connected to the Puppet server. If the Puppet server was connected to a Puppet DB, the reports could have been saved there and could have been visualized on dashboards.